And today I'm going to talk about my joint work with Adam Dor-On, my scientific advisor in Haifa, and Efren Ruiz. Can you see my screen and hear me well?
No, at least I see. And others?
Yes, we did.
Very
See.
good.
Okay.
So this is
I'm sorry. Sorry. Алло?
yes.
Здравствуйте.
What's going
Да,
on?
я сейчас не могу разговаривать, я веду семинар. Так, да, простите, Борис, пожалуйста.
Okay, I decided to tell. This is shifts of finite type is an interesting topic, which is an intersection, which lies on intersection of symbolic dynamics and sister algebras. And I decided to talk about basic facts about these shifts of finite type and to tell what is known about them and their connection to sister algebras, and also present our result, which is new with Adam and Efren, and to present a sketch of its proof. So shifts of finite type is a certain type of dynamical system, and it is a symbolic dynamical system. So it is defined via a discrete combinatorial data, and it is defined by a graph. So let E be a directed graph. And we assume that this graph is without sources and sinks, which means the following. This means that every vertex of its graph receives and emits at least one edge. So E0 is a set of vertices, E1 is a set of edges, of directed edges, and every edge has its source map where it starts and its range map where it ends, and we assume these maps to be surjective. And also I will assume that both E0 and E1 are finite sets. So there is something that we can tell about infinite graphs, but I don't want to cover this today. It's not very important. So shift of finite type is the following dynamical system, where the base, a base space of this dynamical system is a space of the infinite paths. So these are paths which expand to which are infinite to both to minus infinity and to plus infinity. So they're like they do not start or end anywhere. So formally, this can be expressed in the following way. So it's like as a subset of infinite product of sets of edges, which consist of compatible infinite words, and the word is compatible if the source of the next edge is the range of the previous edge. So it's just the space of the infinite paths, and there is, of course, a non-trivial topology on on this space. It is totally disconnected. So this is this space is always is almost always homeomorphic to the counter set, although usually in a non-canonical way. Shift is just a shift where and evolution map is just a shift where we shift every word by one. So for example, yeah, I will give example on the next slide. And the a big question in symbolic dynamics is when two shifts of finite type, it should be T, shifts of finite type are isomorphic for different graphs. And there are actually a lot of examples where of different graphs, such that the shifts of finite type are isomorphic. So this question turns out to be highly non-trivial, and although there are some partial answers right now, there is still no good classification of them. And I will I'm going to describe what is known so far about this classification. And as an example, first of all, I want to describe what does this sign of isomorphism means. Mm-hmm. And this is a usual notion of dynamical system conjugacy. This conjugacy means that we have a homeomorphism between base spaces, which intertwines the evolution map. And this means that the two dynamical systems are basically the same under this homeomorphism theme. This is a strong notion, and for shifts of finite type, they still this notion is harder it is harder to establish this notion for shifts of finite type than a weaker notion of eventual conjugacy. And eventual conjugacy means that although shifts of finite type themselves, dynamical system themselves, may not be conjugate, but when we take a power of n, a power of evolution map, some natural power, then they become conjugate. These dynamical systems become conjugate for big enough natural number. And we need not only for big enough, but for all but finite. So starting from some big enough n, these induced dynamical systems should be conjugate for all n greater than this big N. There is also one more notion, which is the following. So first of all, we should define what's a mapping tori of a continuous time dynamical system. It is a way to canonically assign a continuous time dynamical system to a discrete time dynamical system. We will have a discrete time dynamical system like shift of finite type, then we can just take a product of it with R, and then it already becomes a continuous time dynamical system, because we can shift this part on real numbers, ignoring the first one. But this dynamical system is it is not related in any sense to the initial dynamical system. So we take a quotient of the space such that evolution map becomes the same as a shift in time on like 1 second, say second, or like shift by 1 as a real number. And two shifts of finite type are called flow equivalent if those mapping tori are so of course this is mapping torus, and if there's mapping tori are isomorphic as continuous time dynamical systems. This is a weaker notion of conjugacy, because if two dynamical systems of discrete time are conjugate, then of course their mapping tori are isomorphic. But there are examples where two shifts of finite type are not conjugate, but nevertheless flow equivalent, as well as there are examples of conjugate shifts of finite type which are not eventually conjugate. But now I want to provide an example where we have a conjugacy for different graphs. So we can consider the following two graphs, and it is easy to prove that shifts of finite type for these two graphs are isomorphic. In this particular example, the shift of finite type is that our dynamical system is the base space of this dynamical system is canonically a Cantor set. So how? Let me show that. Yeah, I claim that they are conjugate. And why? Like let us denote the vertices, the edges in the first graph E as A and B. Then B infinite paths are just infinite words in A and B without any restrictions. So we can take any word which is infinite in both directions. This is a Cantor set. But what happens for graph? What happens for graph F? Here, the base space of infinite paths is also canonically a Cantor set, but here it's a bit different, because here it's a sequence of vertices. So at each step, we decide we can either jump from vertex 1 to vertex 2, or stay at vertex 1. And so all B infinite paths look like this. And this is like there is an obvious way to find a homeomorphism between paths of this form and paths of this form. And if we, under this obvious identification, we see that this obvious identification is also preserved by shift homeomorphism. So these two, in this example, our two two shifts of finite type are conjugate, although graphs are different. And there is an algebraic description of conjugacy, eventual conjugacy, and there is even an algebraic description of flow equivalence, but for conjugacy, it is easier to describe. So it was so an algebraic description was provided by Williams in 1973, and the description is the following. So any graph is described by its incidence matrix. So if we have a graph, then there is a matrix such with entries in natural numbers, such that Aij is a number of edges from I to j. And this is an equivalent picture. So, of course, if we have such a matrix, then we can construct a graph. And algebraic description of conjugacy is in terms of these incidence matrices. So let A and B be some essential matrices, and essential here means that there is no rows which no zero rows and no zero columns. And this condition is the same as the condition for graph. No source, no sinks condition for graph. From now on, I assume all matrices to be essential. So suppose that those are essential square matrices indexed by V and W, and let M be some positive integer. So matrices are called shift equivalent with leg M if there are matrices R and S of these compatible sizes with entries in N. This is very important, such that the following four equalities hold. So first of all, we want these matrices to be intertwining for A and B, so they are like homomorphism of ZX modules. And the second condition is the following condition, so that RS is AM and SR is BM. At first glance, this condition is maybe kind of strange, but actually it turns out to be very deep in further analysis. So there is a stronger notion of elementary shift relations. So two matrices are called elementary shift related if their shift equivalent with leg 1. Unlike shift equivalence, so it is not hard to prove that shift equivalence is an equivalence relation indeed. And if A is shift equivalent to B with a leg M, and B is shift equivalent to C with lag M, then it implies that A is shift equivalent to C with lag M plus N. This is a very easy exercise. And elementary shift relation is not an equivalence relation. And we say that they are strong shift equivalent if they are in a transitive closure of elementary shift relation. So transitive closure means that there is a sequence of M shift relation from A to B. So that's it is stronger than ordinary shift equivalence, because if two matrices are strong shift equivalent with lag M, then they are also necessarily shift equivalent with lag not greater than M. So SSE implies SE. This was a definition given by Williams, and he proved the following. So first of all, as I said earlier, by any matrix we can construct a graph such that it is an adjacency matrix of this graph. And by any graph we can construct a matrix, of course. So these pictures are equivalent, and I'll denote the shift of finite type corresponding to matrix just as XA sigma A, because this notation is too cumbersome. Suppose that we have two square matrices, and this is a theorem by Williams. Then shifts of finite type are eventually conjugate if and only if A is shift equivalent to B. Two matrices are two shifts of finite type are conjugate if and only if A is strong shift equivalent to B. And why did Williams even consider this notion of eventual conjugacy and shift equivalence? This is because shift equivalence is a much easier notion than strong shift equivalent. It's much easier to understand. For example, shift equivalence is a computable. So that given two matrices, so there is an algorithm which can say, given two matrices, this algorithm can say whether they are shift equivalent or not. This is not known about strong shift equivalence. And then Williams conjectured that maybe these notions are the same. Moreover, he couldn't, he conjectured that because he couldn't find any counterexamples. And if we see again these two notions, they look quite similar. So it seems possible that given any shift equivalence, we may represent it as a sequence of shift relations. So it was a conjecture by Williams, and it was open for a long time, for more than 20 years, actually, until Kim and Roush found a counterexample. In 1999, they found a counterexample for irreducible and aperiodic matrices, which was at the time examples for more general matrices were found by them earlier. a bit earlier, but finally this conjecture, in final form, this conjecture was disproved by Kim and Roush in 1999, and their example involves two 7x7 matrices. So it's quite a complicated counterexample, and no easier counterexample is known so far. And their proof that this is indeed a counterexample is very complicated. So it involves some very interesting techniques from algebraic topology, and they used some computer algebra computations to prove that the counterexample is indeed a counterexample. Yeah, and so from 1999 there is a big interest in describing this notion SSE, because it is like we may assume that we understand SE very good because we have an algorithm which computes it, and SSE is not that well understood. So for example, it's a big open question whether this notion is computable. And recently there is a new approach to this this problem, and in some aspects it is already proven to be effective. And this approach involves graph system algebras. It turns out that graph system algebras and shifts of finite type are really quite closely related things. So first of all, I recall what's a graph system algebra. So again, if we have a graph, and I still assume here, and I will not allow otherwise, that that our graph has no sources and sinks, and this graph with adjacency matrix A, which must be essential. A Kunz-Krieger EA family is a following collection of operators on a Hilbert space, where there are partial isometries as SE indexed by edges, and projections PV indexed by vertices, such that the following holds. So first of all projections should sum to 1. So this is a non-degeneracy condition. Secondly, domain of a partial isometry should be a projection onto P as E small of projection on its source of its edge, and ranges of partial isometries associated to edges with the same range should be pairwise orthogonal and should sum up to PV. And it turns out that there is a universal Kunz-Krieger EF family, so there is a universal system algebra such that its representations are Kunz-Krieger EA families. This is a graph system algebra, which I denote simply by OA. Actually, this algebra was first defined for matrices by Kunz and Krieger, and then was realized that it is more natural to call it a graph sister algebra, because it's an algebra universal for special representations of graphs. And there are two additional structures that we need on this graph sister algebra. The first one is a gauge action, which is given by the following formula. So gauge action is an action of a circle group on a sister algebra. It should be strongly continuous. And this action leaves projections invariant, and it just multiplies partial isometries SE by the corresponding complex number. Gauge actions for sister algebras are analogs of gradings in algebra. So gauge action defines this because gauge action defines a grading on a dense subalgebra generated by SEs. So we should really think about it as a grading. And the second thing is a diagonal subalgebra. And diagonal subalgebra is a commutative subalgebra. There are several reasons to call it diagonal. One reason is because if we represent a fixed point algebra under the gauge action by a limit of matrix algebras, then this is a limit of diagonals. So diagonal is the commutative algebra generated by the following symbols. And diagonal algebra is very important in the study of this graph sister algebra. For example, when we study when we want to prove that in some cases these algebras are simple, we need to we usually need to do it through this algebra. So this is a relation between shift equivalence and graph algebras. So it was proven by Carlson and Routh in 2017 that two matrices are strong shift equivalent if and only if graph sister algebras are stably isomorphic in such way that preserves diagonal and gauge action. So let me decipher this. So here, this means that we take a stabilization. It is a usual thing that sister algebras are isomorphic only up to stabilization. And here we stabilize the diagonal subalgebra by tensoring it with C0, which is a subalgebra of K. And gauge action, of course, can be lifted to a stabilization. And Carlson and Routh prove that this is equivalent to, so strong shift equivalent is the same as stable equivariant isomorphism preserving diagonals. So we have it's a step towards understanding this notion of strong shift equivalence. But unfortunately, it doesn't help much in determining whether this strong shift equivalence is computable or saying anything particular about it. So there are also a characterization of flow equivalence of shifts of finite type in terms of sister algebras.
Sorry, what does K mean?
K is compact algebra of compact operators.
Ah, I see. Okay. And one more question concerning the partial isometry with index gamma. What is that? I mean, if gamma is a world, is just product or something else? S gamma.
Very
Yes.
It's so I should have written so as gamma is a product, yes.
I see. Okay, thanks.
Ah. Yeah.
And what is OA0?
OA0 is the subspace of elements such that they are invariant under the gauge action.
Oh, see. Thank you.
Thank you.
Yes, this is an almost finite AF algebra, which has a canonical presentation as a limit of matrix algebra. So this diagonal is a limit of diagonals in this matrix algebras. Yeah, so how I may also say how they proved that it is an quite classical result by Renault that isomorphism of algebras preserving diagonal is equivalent to isomorphism of certain groupoids, certain underlying groupoids. And Carlson and Rogers proved that these groupoids are isomorphic if and only if shifts are conjugate. And also gauge action is preserved, it turned out to be preserved automatically from their constructions. For also reducible matrices and the reducible for a reducible and periodic. This is a rather strong condition which so two matrices are irreducible and periodic, I think, when the graph algebras are simple, and matrices are irreducible when for all but finite number of the powers, all the entries are non-zero, and the periodic where in yeah, I think that's okay, I will not tell the exact condition right now about what's reducible and periodic, but it's a rather restrictive condition, and it is equivalent to irreducibility of the corresponding subshift of finite type, so that it cannot be decomposed into the two other subshifts. And they proved that in this case, shifts of finite type are flow equivalent if and only if the algebras are stably isomorphic in a way that preserves the diagonal. So we have an interesting an interesting situation where we can play with those three structures and get invariance of shifts. So if we drop, so here we drop gauge action, and we obtain that isomorphism is equivalent to flow equivalence. And it is interesting what happens if we drop the condition of preserving diagonals. And it turns out that it is not known what happens then, but something is known, and it is the following. So first of all, Krieger, long ago actually, in 1980, gave a characterization of shift equivalence in terms of K0, equivariant K0 groups of graph algebras. So matrices A and B are shift equivalent, and again, the matrices should be essential, and they are shift equivalent if and only if the following group triples are isomorphic. I will not provide you with an exact definition of what's the group triple, but here is just equivariant K0. This is some positive cone there. This is a map, canonical map induced by gauge action. And and he proved that, Krieger proved that this is a full invariant of shift equivalence. And he proved that by expressing this group triple in terms of matrix A and proving that it coincides with some algebraic condition for two matrices being shift equivalent. And for us, it is important that this is an invariant of two sister algebras. So in particular, we see that if two graph algebras are isomorphic in a way that preserves diagonal, preserves gauge actions, then matrices A and B are shift equivalent. But also we know that K0 is preserved under stabilizations, and it is also preserved under homotopy equivalence. So we can say the following. We can say that from it follows that if OA and B are stably equivalently homotopy equivalent, and this means what? This means that the stabilization are homotopy equivalent in a way which preserves the gauge action, then two algebras are shift equivalent. But it's only one side, one direction. So it's only this direction which follows from Krieger's corollary, because it may happen that two algebras have the same K theory. So it is quite, it is not so unusual. And a partial converse is the following, which is obtained by Bratelli and Kishimoto, again, for the very restricted case of aperiodic and irreducible matrices, that for aperiodic matrices and irreducible matrices, we have if and only if. And not only homotopy equivalence, they didn't even talk about that. But algebras are equivalently isomorphic if and only if matrices are shift equivalent. And they, in their proof, they used very complicated classification results, classification of results from the theory of classification of sister algebras. So they just proved that this group triple is a full invariant of the algebra in this periodic and irreducible case. So this follows from some results in classification of sister algebras. And actually, until recent, no one talked about homotopy, and the conjecture was that there is this holds, so this theorem by Bratelli and Kishimoto holds for a periodic for all matrices, not only a periodic and irreducible, but for all essential matrices. But it is still a conjecture, so we don't know whether it is true. But I and co-authors managed to prove a bit weaker version with homotopy. So, so it is the theorem. This is authors. So that for it is in preparation, and I hope will be available on Archive in a few months. So for matrices A and B, essential matrices, again, we have the following if and only if statement. A is shift equivalent to B if and only if these two things are homotopy equivalent. So to decipher it, it means that OA and OB are stably homotopy equivalent in a way that preserves diagonals. And I want to explain briefly how this result was obtained and what led to this result. And this requires new techniques from involving some viewpoint of C-star correspondences and even higher categories. So let me show what it in a coincide version. So first of all, I'd like to define C-star correspondences. So a correspondence is a right Hilbert A module. And what is a right Hilbert A module? It is a Banach A module, right Banach A module, together with some inner product, which mimics the definition of Hilbert space inner product. So it's like a Hilbert space, but with values in a sister algebra. So it's like a non-commutative analog of Hilbert spaces. And a Hilbert, so we can, as for Hilbert spaces, we can define adjointable operators between them. So a bounded alien operator from X to Y is called adjointable if there is an adjoint, which is defined as usual. And the space of adjointable operators is defined like this by LXY. And in case of LXX, so LXX is a sister algebra. It is a particular and a correspondence is a special type of bimodule, of BA bimodule. So if B is another sister algebra, a BA correspondence is a Hilbert A module. So it's a right A module together within a form with values in A, together with a left action of B by adjointable operators. And since B is a sister algebra, this should be compatible with taking adjoints. So it should be a star homomorphism. So it's like a bimodule as in the like ring theory, given two bimodules, with two compatible bimodules, we can form a tensor product. So if Y is a CB correspondence, we can form a tensor product, which is a CA correspondence, Y tensor over BX. And we can, there is an inner form which is similar to the definition of tensor product of Hilbert spaces. So it's indeed, the result is indeed a CA correspondence. Yeah, let's move forward. So, and we also need a notion of isomorphism, and by isomorphism of two correspondences, I mean just a unitary isomorphism of bimodules. And an example, and basically this is the only type of correspondence we need, is a graph correspondence. So if R is any matrix of size V times W, we can consider two finite dimensional commutative system algebras, one of dimension V and the other of dimension W. And to a matrix, not necessarily essential, but in everything we consider it will be an essential matrix, we can, so it should be XR. To matrix to matrix R, we associate XR, which is a direct sum of the following vector spaces. For each pair VW, the vector space of what dimension RVW. And the left and right actions on XR are defined the following way. So here we, so delta V is a projection onto the spaces corresponding to vertex V, and delta W is a projection on right on the spaces corresponding to the vertex W. So actually every correspondence between A and B is of this form, and this is correspondence which is associated to a matrix, and a tensor product of such correspondences is the same as a product of matrices. So if we have some other matrix W of compatible sizes, then the tensor product correspondence is the same as correspondence associated to their product. So in particular, yeah, a graph correspondence is a correspondence, say, is a graph correspondence associated to a square matrix. It's and then we need a notion of transformation. So transformation is the following thing. So we are provided with the following data. We have two correspondences. X is a correspondence over A, so it's an AA bimodule. Y is a correspondence over B, and a transformation is an AB correspondence, which contains something like an action of X. So with the following unitary isomorphism of correspondences. We can so transformations are like correspondences between correspondences, and if we take another transformation which is compatible with the previous one, then we can compose them, and we can consider a tensor product transformation. I call them composition because they are like morphisms, and I will elaborate on it a bit later. So we can take the tensor product, and also if we'll play with some diagrams given two maps psi g and psi f, we can get an induced map psi j dot psi f. For any there is, for example, the following transformation: x tensor with the self n times, and eta n, which is defined as the following natural isomorphism. So these two are, of course, canonically isomorphic to x tensor n plus 1. And a homotopy between two transformations. So there is a more general notion of homotopy, but it's quite complicated, and like a bit simplified notion, which is enough for the theorem, is the following, where if we have two transformations with the same base correspondence, then a homotopy is just a homotopy in this unitary, is in the space of unitary maps connecting psi g and psi g prime. And there is this information is a part of definition of a bicategory, so like a two category, where elements are pairs of algebra and correspondence over it. Morphisms are transformations. So a morphism from B to A is a transformation from B to A, from BY to AX. And compositions are tensor products. So this is a composition. And two morphisms are isomorphism transformations. So this bicategory was introduced by Ralph Meyer and his students. And this particular definition was coined in the paper of Meyer and Camilo Zenem in 2017. And what is good about this definition is that in this bicategory, the construction of graph sister algebra becomes functorial. So roughly the theorem is the following, but I don't include all the details because they are quite cumbersome and complicated. Because in general, this high category theory involves a lot of conditions under the, so a lot of complicated conditions. So let CT be just one category, and in the paper we say that it is a bicategory, but let it be the following category, where objects are sister algebras with T action. So like with like graph algebra with gauge action, and morphisms are inner conjugacy classes of equivariant star homomorphisms. So this like inner conjugacy classes is a bit tricky, and unfortunately we need it because like some universal constructions are unique only after some inner conjugacy. This usually happens, and therefore we should identify morphism after inner conjugacy. but we only study equivariant star homomorphism, and it turns out that there is a functor. Actually, it comes from some bicategorical functor, but I don't want this right now. And there is a functor from Cn, and it is Cn. I want to recall that it is this bicategory of transformations, which maps OC0 0A XA to its graph sister algebra, and this functor is called a functor of Kunz-Pimsner algebra. And I now understand that for it to that I forgot that it should be not just a way, but it should be a stabilization. Because otherwise this will not work as I wrote here. Yeah, so here we should take stabilization. So there is a functor such that Kunz-Pimsner algebra functor. So this functor is called a Kunz-Pimsner algebra functor. Such that it maps graph correspondence to the Kunz-Pimsner, to Kunz-Krieger algebra of a graph, to a graph sister algebra. It maps this unique transformation, and recall that transformations are morphisms, so it maps morphisms to a morphism, to equivalent homomorphism between two algebras. So it maps these canonical transformations to isomorphisms. This is like a universal property for this functor. And a homotopy between transformations induces a homotopy between the images under O. So this is, by this part, it is Meyer-Zeine in some way, but I modified their result to suit my needs. And here it is our result. And what can we obtain from it? So we obtain from it the following. So first of all, and here I should switch to writing. So recall that we want to prove that shift equivalence imply homotopy equivalent homotopy equivalence. So for that we have to recall the definition of shift equivalence. So I recall that two matrices are shift equivalent if there are matrices R and S such that AR is RB, SA is BS, and RS is AM, and SR is BM. So in terms of graph correspondences, and I recall that product of matrices, so let me show you here. So products of matrices goes to tensor product of correspondences. So on the language of graph correspondences, this means that if we consider this thing, COA, and x of A, we consider two pairs, which are objects of our by category. And we have the following isomorphisms. So we have isomorphism XA tensor XR R to XR tensor XB, which is the same, which is an isomorphism defining transformations, if you recall. So we will denote it by psi r. They're also the same for S. We'll write it like this. So it will be XB tensor XS to XS tensor XA. And there are also isomorphisms of XB tensor XR tensor XS to XA tensor power and XS tensor XR to XM. So we have the following four isomorphisms of correspondences, and this is actually the same as shift equivalence on the language of correspondences. The first two morphism means that we have transformations. So we have the following transformations. So we have a transformation from here to here, which is XR with psi R. We have a transformation here, which is XS psi S. And this induces via O, via this Kunz-Pimsner functor. This induces equivariant maps between stabilizations. So OA gamma A, this induces something that we can call O R psi R. This is an equivariant map, or to be, if we are going to be precise, it is a class, an inner conjugacy class of equivariant maps. And here is the same for S. And then turns out that using two other maps, we can construct a homotopy of their composition with this isomorphism correspondence. So it turns out that, first of all, so their composition let me write it. One moment. So it turns out that XS psi S composed with XR CR is a homotopy equivalent as a transformation to XA tensor M. No, here should be B, but the same for A with other direction. Psi, no, that's that canonical map. Eta M. And again by O, and third part of the theorem, this induces a homotopy equivalence between equivalent homotopy equivalence between two algebras. So this says that this composition by functoriality, this says that this composition is homotopy equivalent to this map which is by the second part of theorem is an isomorphism. So a composition of two morphisms is homotopy equivalent to a isomorphism, and the other composition is also homotopy equivalent, but to OXAM at M. And this is how, using like higher categorical functoriality of this construction of graph sister algebras, we were able to prove that graph sister algebras are homotopy equivalent if the corresponding matrices are shift equivalent. And this how we proved eventually if and only if statement, which was shown by me before, because the if statement was followed from Krieger theorem. And this is one step closer to our understanding of strong shift equivalence and its relation to sister algebras. So I think that's it. Thank you for your attention.
Okay,
Thank you.
thank you very much for the very interesting talk. And now questions. So, Anar, of course you have.
Yeah. Thanks for interesting talk. I have a question concerning the result of 2070s. That was a criteria. As I guess the one of the authors was Lord, right? I forgot the other one.
Lord, I don't know. Williams, 1973, I think.
No, 2017s. 2017s, they were resolved. Ah, yes, this one. Yes, Carlson and Rowe. Yeah, A and B strong if equivalent if and only if. Yeah. Does it mean that the Kunz algebras they are isomorphic as an operator systems? I mean, if you lift this tensoring by K, it doesn't mean that if you pass the matrices, you have a complete isometry between them and preserving the positivity or complete positivity. Is it true, something like that, or not, or is different?
Like you mean without stabilization or what?
No. The sister algebra is also like operator system, right? So you can pass the matrices instead of tensoring, as I guess it does. It just means there is a complete sort of isometry between these Kunz algebras, OA and OB. But it may be wrong, sure.
So every star homomorphism is automatically completely positive.
Yes, but it's not I mean, not exactly homomorphism. It just there is an order isomorphism preserving the order between this OA, OEB.
And if you have a complete isometry between C-star algebras, they're automatically they're automatically star isomorphic. This is a result of Arvidsson.
Ah, yes. Is it? Ah, sorry, I didn't know it.
Yeah.
So, but that doesn't mean about the matrices, right?
I should say, sorry, you're right. Only for a unital complete isometry. If you have something with matrices, if you tend to stabilize, maybe this is not so clear.
I see. But this result not is all about this one, right? Not is all about complete map.
This is just about star isomorphisms.
I see. Okay. Well, I thought that there is another result by Krieger, right? So preserving positivity. I thought that it's all sort of about complete positivity. Because there was a certain cones there. There must be sort of positivity.
Yeah, I mean, part of the data that you have in K-theory is the positive part or the monoid part in K0. This is a standard part of the invariant, but it's about abelian groups and monoids. It's not about algebras or operator systems.
Okay, yes, I got it. Okay, yes, thanks.
Okay. Other questions? Maybe Alexey Yulich has a question.
Well, I'll just I have a question about the very beginning, about the first conditions of on your graph. So why is it natural and why is it essential to require that the range and the source maps are surjective?
Because we consider B infinite paths. So if the vertex is either source or a range, then there is no by infinite path which passes it, because nothing can either go into it and go out of it. So it will be like we can the shift of finite type will not change if we just throw every single source out.
Thank you. I see.
Okay. Other questions? Yes. And Renat, where is him? Renat disappeared. Yes. Our last.
Renat is here.
Yes. By the way, many times I wanted to say that your talk was also very good and clear, etc., like this talk. So our last talks are perfect, in my opinion. So gentlemen, so I wish everybody to be healthy, and with God's permission, we shall meet next year. So far, Happy New Year to all of us.
Yeah.
Yes, and
thank you.
Yes, and continue our contacts. Again, thank you very much for your participation. Yes, and bye-bye. Okay.
Ladies and gentlemen, please.
Yes, ladies and gentlemen, yes. Thank you very much. You're right.
Thank you.
Okay.
Thank you.
Okay,
Thank
bye.
you.
Bye.
Thank you.
Goodbye.
Bye-bye.